Let me put it this way. And we do something very simple. We do an iterative refinement. Initially, all vertices get the same color. And then in every refinement step, we look at two vertices, well, all pairs of vertices, and we assign different colors to them. If for some color, they have a different number of neighbors of that color. Okay, so in the first step, every vertex gets colored by its degree, basically. And then it moves on. I'll show you an example in a second. Okay, we do this until the coloring stays stable, and that means the partition of the vertex set into the color classes no longer changes. We don't actually care about colors. We only care about the partition colors, just a convenient way of thinking about this. Okay, and this is the one-dimensional version of this Weisfeiler-Leman algorithm in the title. And I come to the higher dimensional in the second, but let's just look at this example. So there's a graph. Initially, all vertices have the same color. So what happens in the first round? Now I would have, okay. Look at this. Do we have a pointer, anything? Okay. So look at that's the vertex of degree 4 up there. So that has 4 blue neighbors. All others have degree 3. So they have 3 blue neighbors. So we should have 2 colors now. This one vertex is red. All other vertices are blue. But now things change. For example, it does work. Okay. So these vertices, thank you. They all have a red neighbor, so now they should get a different color from, say, that one, which only has blue neighbors. Okay, so that happens. They get different colors, and now we have to consider, for example, this one has 2 orange neighbors and 1 blue. This one here has 1 orange, 2 blue, so they should get different colors. Okay, and it goes on like this, and eventually, I think we have reached a stable state there. And since I'm not touching this because I don't know how to go back, so let's just believe that this is the stable. Okay, that's how it goes. So basically, we color the vertices by some kind of iterated degree sequence. Okay, I was right. Now. What I really want to look at is the higher dimensional version of this, where instead of vertices, we color k tuples of vertices.
So here you don't care like in the usual graph coloring, you care that the vertices, the neighbors don't have the same color, but you don't care.
No, color is just a name for type or whatever. It's or for an equivalence class. Color has no meaning in any way. Yes?
Sorry, on a 3 regular graph.
Nothing happens.
Okay, good. Thank you. So if I wanted to do this good on a 3 regular graph, I have to do this, right?
Yeah, you have to do something. So on a regular graph, nothing happens. That was a good sanity check, and I can show you some other examples, but I don't want to spend too much time. Now, higher dimensional version. We color k tuples in basically the same way, except that it's a bit more complicated, and this was introduced by Weisfeiler-Leman in 1968, but only for pairs, and then later Babai generalized it to k tuples. Yes?
Tuples ordered or unordered, or it is not important?
Ordered. It's important. Okay, I'll give the precise definition now. It's a pain, but I want to go through it since I'm talking about it all the time. So let's just do this, okay? So we pick some k greater than or equal to 2, and we want to color k tuples. Okay, so what's the initial color? Well, we look at the local structure we see on the tuple. So 2 tuples will get the same color initially if they have the same equality type. So if the first 2 vertices are the same in one tuple, they need to be in the other tuple, and if the same. So basically, if the ordered graphs on these 2 tuples, the ordered induced subgraphs are the same. Okay? So that's the coloring we start with. And now in a refinement step, we have this thing. Again, I'm saying, when do two tuples still get the same color in step I+1? Okay, so what's the condition? First of all, they need to have the same color in step I. So once they are different, they stay different forever. And then I'm saying for all colors that I already have in step I, the following must hold. Now, in the one dimension, the color refinement, we said for each color they have the same number of neighbors. Now, what might be neighbors here? These are tuples that we obtain by replacing one coordinate. Okay, now we have k types of neighbors, replacing the first coordinate, replacing the second, replacing the kth. So we look at all these separately and then say, for each color that we already have, they must have the same number of neighbors of this sets. So the same number of vertices I can replace for the first vertex to get color C1, I must have for both the V tuple and the W tuple. Then I'm replacing the second coordinate again for each color C2. It must be the same and so on. Okay, that's how it goes. And then we iterate until the equivalence relation of the K tuples no longer is refined and it's stable.
Why do you stop here? Because it would be more natural for every color to look at all subsets of K.
Yeah, that would make a difference. It would make it, you know, you can simulate this.
Okay, you can simulate it.
That would make a difference.
That would be the natural
It's
next.
fairly robust. And actually it had many different characterizations. But again, I don't want to get into to it. Okay, so that's the algorithm. And let me just show you one simple example to see how it goes. So we want to apply it to a cycle of length 8, I suppose. Okay, so what do we do? What's the initial coloring? Well, we have 3 colors. We basically have the color where the 2 entries of my pair are the same. So that's the darker green. Then we have the color that the 2 entries of my tuple are connected by an edge. Since it's undirected, the colors here at this point are also undirected. And we have all the rest, no edge between them and different. Okay, that's the 3 initial colors we get. And now let's see how we go on. Let's look at this pair, the top vertex and that one. Well, they have one common green neighbor. If we look at the pair consisting of this and that, they don't have a common green neighbor. So they should get different colors now. If I compare this tuple to this tuple, I don't see a difference, right? No common green neighbor, that's all I see. So they stay the same. So that's the new coloring we get. We get one new color, and then in the next step, it turns out we see everything, all possible colors. How do I know that these are all possible colors? Well, in this case, it's very simple. It's just the orbits of the automorphism operating on the pair, so I can't get any finer. Now, in general, it doesn't happen that I see the automorphism. If I could see it, I could solve graph isomorphism in time n to the whatever my dimension is. Now, here's also a special thing that all colors are symmetric. This usually also doesn't happen, not even in undirected. So this is very special, but it's kind of the only example I can reasonably explain in a talk. And if you want to do examples for this, in particular for higher dimensions, it's really difficult because you have so many colors, and you see like all combinatorial things in graphs you usually see, say, with 3 dimensions. So it usually subsumes all isomorphism tests that are combinatorial, basically. But again, that's a different talk. Okay, Weisfeiler-Leman originally came up in the context of graph isomorphism. For example, it plays an important role in Babai's quasi-polynomial-time algorithm, where he runs it with dimension log n. It also plays an important role in all practical isomorphism tools. Okay, then it has logical characterizations. This has been known for a long time. So basically it's an equivalent test for certain logics. We have game characterizations in the style of Ehrenfeucht-Preissé games. We'll see a bit of them later. But the surprising thing is it also has connections to machine learning, which is quite interesting and really surprising to other things like linear programming, combinatorial things like counting homomorphisms. For example, two graphs get the same coloring scheme if the number of homomorphisms from all graphs of tree width at most k to these two is the same. Okay? And it has some connections to proof complexity that we explored with Christoph Bergholz. Basically, lower bounds for this algorithm give us lower bounds for things like polynomial calculus on a formalization of graph isomorphism. Okay, so that's why many people have looked at this algorithm in recent years, and it has received quite a bit of attention. But there was some basic question that was open for a long time, and that is how many iterations do we need? Okay, and that's the question I want to address here. For how long do we need to run this? Okay, and that's what all of the rest of the talk is going to be about. Let's just review what we know. So we have some trivial things. Let me start there. Basically, we have a partition of n to the k elements. We refine it so we have at most n to the k minus 1 steps. And now I have 3 columns here for k equals 1, k equals 2, and greater than or equal to 3, you'll see. Okay, so let's look at the first one first, just color refinement, the 1 dimension. So at most n minus 1 steps, it's kind of easy to see that you need a linear number of steps. You just run it on a path and the colors propagate to the middle. So you need roughly n over 2 steps. But actually, you can get to exactly n minus 1, as Sandra Kiefer and Brandon McKay showed not so long. Okay, so that's the case of the one-dimensional case. You get the maximum number of possible iterations. Now, surprisingly, for 2-dimensional, this doesn't happen. And this was first noted by Sandra and Pascal Schweitzer a couple of years back. So they went below n squared, right? Okay. Now, then something really surprising came. Actually, n rounds are enough instead of the n squared. That was proved by Moritz Lichter, who is also of these papers, and Ilya Ponomarenko and Pascal Schweitzer. Okay, so that was really nice. And then we were quite puzzled what to expect. I mean, this question, how many iterations we need, was around for a long time. Essentially, Fürer proved in 2001 that you need at least a linear number of iterations. That's relatively easy to see, at least with our understanding now. But you know, after this result, we were really wondering what the right answer might be. It's really not clear. Okay.
Is it all one? It were 18 years before Ponomarenko.
Hmm?
Oh,
Yeah, that's 2001. Oh, okay. Yeah. Okay. So that's where we were. And again, for the k-dimensional, we also didn't have anything better than linear. Okay. So then, generalizing this upper bound, we proved an upper bound of n to the k minus 1 times log n. Okay, I'll speak a little bit about that. But lower bounds are the main thing, and there's something was known. Christoph Bergholz and Jakob Nordström proved that you need n to the omega of k over log k rounds, but only on relational structures with k-array relations. It didn't tell us anything about graphs, unfortunately. So that was a really nice proof that actually went through proof complexity. Okay, so first we improved this. We got rid of the log factor, which was not so spectacular, I guess, by kind of looking a bit closer at this technique. And then the most recent result is that we proved by different techniques that you can get actually a low amount of n to the k over 2. Okay, and that's the main thing I wanted to.
For graphs.
For graphs, yes. So these two were for k-array relational structures. This one worked for graphs. Okay, so we're kind of close to the upper bound. There's still a gap, and I have no idea how to close this gap, but that's another story. Okay, so let me first briefly look at the upper bound. The proof is really beautiful, and it basically, our k-dimensional version is just adapting the proof for the k equals 2 case by Lichter, Ponomarenko, and Schweitzer. So we have this upper bound that all holds on graphs as well as all relational structures. So that has nothing to do with it. And the way it goes is we translate the sequence of colorings we get in the iterations to a sequence of semi-simple algebras, matrix algebras. And what we need here is n to the k-1 by n to the k-1 matrices. Okay, so we have these matrix algebras. And then basically, facts from representation theory tell us that such a sequence of matrix algebras, semi-simple matrix algebras, cannot be longer than essentially the dimension of the matrices. Okay, and we use that, and that gives us the result. That's basically how it goes. And that's all I want to say about this. But it's surprisingly non-trivial. And I don't know of a direct combinatorial proof of this. I only know this proof going through representation theory. Yes?
Are the cases for all different k just completely separate, or can there be a reduction between, let's say, k equals 3 and k equals 4? That if there is a surprising upper bound for 3, something for 4.
I mean, you could say it's kind of a reduction what we do, but actually, I mean, it's you need to construct the right algebra. And once you see it, it's clear it's always the same argument, and it's not worth formulating it as a reduction, I suppose, although it may be. Okay, so now let's look at the lower bound. So we get a lower bound of n to the k over 2 even on graphs. And I have to be really hand-wavy, and some of the things I'll be saying are explicitly wrong, but I'm just trying to convey kind of the main idea how we do this. So we start with basically what Fürer did. And there's these Fürer-Leman gadgets, which you may have seen. So basically we have a graph here, which is a 2 by 5 grid. And we replace every node of the graph by a gadget like this, and every edge by basically 2 edges. And these gadgets have the property that you can kind of flip these outgoing edges, but you always have to flip an even number. So that's the automorphisms of the gadgets. So at every node, so you can flip this one and this one at the same time. That would be an automorphism, but you cannot flip all 3. You can only flip an even number. That's the property of these gadgets, and it's essentially the same thing as in these citing constructions, right? It's exactly that. Or it's an encoding of XOR formulas by graphs, if you will. Okay, and then basically we consider another one of these where we flip one pair of edges. So flip the connection. So we have, where it's parallel here, we have a cross here. And the nice thing is we can shift this flip through the graph. Okay, so basically if we look at these gadgets, well, we can exchange these two and these two at the same time, and the cross moves there. So we can move it around, and that's why it's kind of hard to see. That basically means if you have a system of linear equations, as long as something is free, you can always move it around. That's what happens. And then basically, if we want to distinguish them, we would, I mean, this Weisfeiler-Leman corresponds kind of to moving k pebbles over the graphs until you detect the difference. And what you would do here is basically you would start here using 3 pebbles and shift it to the other end. And at some point you have captured this twist and then you have distinguished them. Okay, so with 3 pebbles, and that means in the 2-dimensional version, you would be able to distinguish these two. Okay, but again, this is very hand-wavy and I'm not going to get much more specific. Now, one thing we do is we look at an abstraction of this. So basically what we want to do to distinguish these 2 graphs is we want to capture this twist. Okay, and so we play a game on this where we move the pebbles actually on the 2 graphs that I had before. And instead we say, we look at a graph search or graph capturing game known as robber and cop game on this one underlying base graph, where we just have k pebbles or k cops capturing a twist or a robber. Okay, so this is, say, a position where we start and the robber is sitting there, the twist is sitting on this edge, and then we put another cop player there or pebble up here, and now the robber needs to get away because he doesn't want to be caught there. So the robber can move along the path by shifting these twists. So the robber now may move there, and then we maybe continue like this and slowly close in and eventually catch them. Now, if we want to do this on this type of graphs, we basically need number of rounds linear, basically related to the length. We have to search through this. We can start in the middle, makes it a bit shorter, but essentially we have to go through the grid. We cannot jump very much. Now, of course, that gives us a linear lower bound. That's basically how Fürer got the linear lower bound. Okay, and now we want to improve this. And the way we do this is, the basic idea is we reuse the gadgets. The idea would be if 2 of these CFI thingies are very far apart, then they should be kind of independent. So we can identify them and still play the game. That's the idea. It's just not so easy to make it work. Okay, so basically we're in a situation like this, and let's say this and this is far apart, and we want to identify them. And in our original graphs, so that's in the abstraction, in the original graphs, we just identify them pointwise. Okay, and then the idea would be we do this quite often, so to get a small graph, but the game is just the same as the original. We still have to play through the whole original grid, basically, to win there. Okay, so how can we achieve this? And now it gets really shaky. And what I say on this slide is not fully correct, but I think it gives some idea. So basically, we have this grid. Basically, the height of the grid is the k, and the length is some number to be determined. And then on each row, we do these identifications, and we do them in a periodic way, but the periods for the different rows are distinct. Okay, and basically, imagine we take a prime for each row, which is the period of that. Now, that's not true. What we actually do is we take a prime for each row, and then the period in row 1 is the product of the primes of rows 1 and 2. That's a technical thing, but for now, let's just look at it this way. So in row 1, we have prime 2, 3, 5, 7. Okay, and now in general, we want to start with some n and then take many primes between n and n over 2, so that product will be something like n to the k. Okay, and that will be the length of our grid. Okay, so basically here, the actual length of the grid we take is 210, product of all the primes. So why do we do this? Basically, we want to move a separator, so the cops want to move systematically through the grid. They have to cut somewhere and then shift this cut. And now, as long as we have no repetition in the periods, when we move, well, okay, a cop that appears here now actually appears here and here and here and here, because we have identified all these, yes?
Can you think of this as writing down the row that the cops are in Chinese remainder representation?
No,
No? Oh, okay.
I wouldn't think of it like that. I don't think so. It's probably you can, but it doesn't get you anywhere.
Cause it's like they're in.
Yeah, look, it's probably so, but that's really not the point. So you shouldn't think about this, but just how to see what remains of the original graph. Okay? I mean, it's just we have these numbers. The product is large, so that's the Chinese remainder thing. But now we look at these periods. So if I put a cop here in the graph where I have identified all this, it appears in all these places. Same for the other rows. Now the separator also appears in many other places, but it's not a separator there. As long as they don't fit together, which only happens after 210 steps, it's never a separator. So basically these other things don't help me because they never separate. And to move the separator, I can only go step by step as I did before. If I make a jump, something will go wrong. That's kind of the key idea. Okay, so I've illustrated it here again. Let's say I'm standing in this position and now I move here. So what will happen is, oh no, I've moved here. Okay, the new cop appears. Now I remove the old one. And suddenly I have basically an escape path through the whole grid. So basically I'm lost. So I can only move step by step. And that's kind of how the proof goes. And then it gets quite technical to get this right, but I don't have the time for this. So that's basically it. Let me just close with two open questions, which I both find very interesting. The first is, of course, what is the exact, oh, this is supposed to be n to the k over 2 or n to the k minus 1. I would lean towards the k minus 1 as the correct answer, but either way may be possible, and I don't know which one. The second would be very useful for various applications of this, and that would be to have more robust bounds. So I want to find such graph that can be distinguished by the k-dimensional version as my grids, but even if I play f of k, say 10k dimensional version, I need many rounds. Okay, now for the k-array relational structures, we have a result like this. For graphs, we don't. That would be very useful, and I think the next talk is a little bit about this, so maybe we'll hear more about this. Okay, that's it. Thank you.
Yeah. Okay, let's move to the next talk. Thank you very much.